Hey Precalculus, this is a new video for you. 3.1 notes. We're starting to talk about functions a little more in depth, and I'm going to start with domain of functions. So let's first kind of pin down what I mean by domain. Well, domain in an informal sense is where the x values of a function live. It's where the x values of a function, and if I'm talking about a function, I'm talking about like f of x. And you probably recall range is just it's not where the x's live, but where the y's live. Same, but with y values, which are also called the output values. It's sort of like x corresponds to y, but x also corresponds to f of x. So f of x and y are kind of the same thing. So where would a function not be able to input somewhere? Well, I think we already kind of have an idea for that from the graphing sense chapter. Asymptotes, right? So fractions. Whenever you have a fraction with variables on the bottom, you are opening yourself up to asymptotes or even holes in the graph. So asymptotes or holes in the graph live in rational functions or fraction-based functions. So, divide by zero errors, your domain does not jive with that. Divide by zero errors. So that's going to be a domain issue. There's your first domain issue. Your second domain issue are even-rooted functions. So think about this. Even roots don't have real solutions when the inside of them is negative. So even roots must be greater than or equal to 0, right? Inside the root. So the x's can't live where an even root's negative. X's can't live where even roots are negative. That kind of rhymes. And of course, I'll show you examples of these. Maybe I should show some examples right now. So for fractions, it's kind of like if you saw a function f of x equals 1 over x squared minus 4. Something like that. You can't divide by 0, so this function, your x's cannot be 0. So if you factor this plus or minus 2, yeah, x can't be plus or minus 2. So the domain would be, yeah, this function can live everywhere, except it can't live at plus or minus 2. And for even roots, if you had g of x is equal to the square root of 4 minus x squared. Actually, that's not a good one to start with. How about just 4 minus x? Much better. You could say something like, hey, the inside of this must be greater than or equal to 0. The domain cannot go out of those boundaries. So you could solve this inequality by adding x to both sides. You get 4 is greater than or equal to x. Probably better to talk about it in terms of x on the left-hand side. It's x is less than or equal to 4. This tells us that the domain of this function can be from negative infinity to 4, but that's it. So this is the domain for that, and for this the domain would be everything but plus or minus 2. So you could say all reals except x can't be plus or minus 2. All right, I'm kind of going off script here, so let me try to reel us back in. So those are the two big situations. The other thing I wanted to talk about are the questionable ones. Usually people are like, what the heck is going on with odd roots? So we talked even roots. How about odd roots? And we'll talk about something like, let's say h of x is equal to the fifth root of 7x plus x cubed. Something pretty random like that. Well, the way odd roots work is that, I can take the fifth root of positive 32 and get 2. I can take the fifth root of negative 32 and get negative 2. It doesn't matter if my fifth root is even or my fifth root is if my fifth root is positive or if my fifth root is negative. It's fine. So, odd roots, unless there's a problem with like an even root nested inside of it or a fraction nested inside of it, there's no domain issues that are inherently tied to the odd root. What about absolute value functions? We saw a little bit of that last chapter. So something like, k of x is equal to the absolute value of x squared minus 4. Well, sometimes students say, hey, maybe we should set that thing equal to 0 and see what's up. But if you do that, all you're doing are finding the places where it crosses the x-axis. The graph of this looks like a parabola that's normal except between negative 2 and 2. Between negative 2 and 2, the parabola is flipped upside down. This is actually something we were going to talk about in the last chapter, but we're kind of running out of time with the new way in which I'm teaching this year. Yeah, it basically is doing this between negative 2 and 2, and then it's doing this beyond that. So, I'm not saying you needed to know what this function looks like, but I'm saying there is no domain issue with this graph. Every single x value is accounted for. So, for absolute values, unless there's an even root involved and a fraction involved, there are no domain issues. And I probably, I could probably talk about several other situations, but I think I'll just leave it at that. Odd roots, there's no domain issues. Absolute value, there's no domain issues. And actually, let's do one more. And one more. What about just good old-fashioned polynomial functions? So I'm saying like any function that can be presented as like x to the fifth plus 7x squared plus 2. Something like that. Something in which there's no negative exponents, there's no fractional, there's no rational parts to it where there's an x on the bottom, there's no even roots, there's no odd roots. It's just straight up maybe something like that. Now again, if you try setting it equal to 0, all you're doing are finding the zeros. The zeros that live on the function. There's no domain issues. All right, so I've mapped enough of this out. I'm wondering if I should just stop the video now and do the examples on the next one. Yeah, let's do that. I think you guys have gotten a good enough overview of it where now we can dig in with some context. Hey, thanks for watching.